Yes, let's see question number 15 of HCRMA. Suppose an attractive nuclear force acts between two protons, which may be written by the expression F is equal to C times e to the power minus kr divided by r square. A part is write down the dimensional formula for and approximate SI units for C and K, and B part is that suppose that K is equal to 1 Fermi inverse and the repulsive force between two protons is just balanced by the attractive nuclear force when the separation between them is 5 Fermi. Find the value of C. So basically first part is based on dimensional analysis. For we need to find dimensions of C and K. Now let's consider the dimensions of K first. E to the power minus kr is a format of e to the power minus x, where power of exponent is always dimensionless, as we have learned in mechanics, as we have learned in dimensional analysis. So K into R should be dimensionless. If K into R is dimensionless, R has a dimension of meter, so K has to have a dimension of meter to the power minus 1, or K has a dimension of K has a SI unit of meter to the power minus 1 and a dimension of L to the power minus 1 as depicted by the above part. For the dimensions of C, let's consider it further. See, force is actually C into e to the power minus kr divided by r square. So C can be stated as F into r square divided by e to the power minus kr. Now F has a dimension of Newton, r square has a dimension of meter square, and e to the power minus x or e to the power minus kr is again a dimensionless quantity. So basically this particular thing has a dimension of Newton meter square, or SI unit would be Newton meter square, and Newton can be written as ml2t mlt minus 2, and meter square can be written as L square. So the complete dimensions of this particular part comes out to be m L cube t to the power minus 2, which would be the answer to the first part. In the second part of this problem, we have been asked the value of C. In the second part, it is given that we have two protons plus E and plus E, which have where E is equal to 1.6 into 10 to the power minus 19 coulomb, which are kept at a separation R is equal to 10 to the power, R is given to you as 5 Fermi, or 5 into 10 to the power minus 15 meter, and it is stated that F repulsive due to the electrostatics is actually equal to F attractive due to nuclear forces. Now if we see, write down the repulsive forces can be written as 1 by 4 pi epsilon naught. Q1 can be written as 1.6 into 10 to the power minus 19. Q2 again can be stated as 1.6 into 10 to the power minus 19. So over here we get a square term, and R square in this case is 5 into 10 to the power minus 15 whole square can be written as C into e to the power minus kr divided by r square, which can be written as 5 into 10 to the power minus 15 whole square. Now these two terms get cancelled out over here. So C in this particular part comes out to be 1 by 4 pi epsilon naught can be written as 9 into 10 to the power 9 into q square can be written as 1.6 into 10 to the power minus 19 whole square divided by e to the power minus k into r. If I extend it in the next page, C comes out to be equivalent to 9 into 10 to the power 9 into 1.6 into 10 to the power minus 19 whole square divided by e to the power minus K into R, where K was given to you as 1 Fermi inverse and R was given as 5 Fermi. So K into R basically becomes equal to 5. So C in this particular problem comes out to be 9 into 10 to the power 9 into 1.6 into 10 to the power minus 19 whole square by e to the power minus 5, or 9 into 10 to the power 9 into 1.6 into 10 to the power minus 19 whole square into e to the power 5, where E is Napier's constant over here, whose value is 2.713. So this part can be written as into 2.713 whole square, and if we calculate this particular part, the outcome which we get is, this is roughly equal to 3.4 into 10 to the power minus 26 Newton meter square, which would be the answer to this problem.